Hola amigos, bien o no, mis saludos desde Inglaterra. Hoy es un día con un clima poco fuerte hoy, mucho viento, lloviendo, mejor para ser aquí en la casa y leyendo. Y por eso yo quiero compartir otra leyendo con parte de este libro, Einstein's Universe, by Nigel Calder. Este es publicando en el año 1979, casi 50 años antes. Busca para explicar en una forma muy fácil la teoría teórica del Albert Einstein, de relativity. Un parte es una con la historia de ciencia, pero también podemos escuchar un ejemplo con muy buena forma de estilo escritorio y también para mejorar nuestra escuchando y nuestro vocabulario. Entonces, ese es el tema de hoy. So, hello again from England. Weather's a bit moody today. It's very windy, it's raining, not very nice. So, better day to be indoors reading a bit. I'm going to share with you a reading from this book, Einstein's Universe by Nigel Calder. This was originally published way back in 1979. This book ambitiously looks to try and explain in easy English Einstein's theories of relativity. But quite apart from that being a book on like the history of science, it's also an interesting kind of style of writing. So I'm going to share some of this with you now, really just to see again how well you understand it. Look, there's new vocabulary. Look at some of the patterns he's using, some of the phrases, because it's a fairly easy style. So in this section I'm going to read you here, he's talking about how where you are, your position as an observer of an event, or in this case an object like the sun, where you are relative to the object can change what you see compared to my view of the object if I'm standing in a different position. But let's let him do the rest of the explaining. So this is part from chapter 2, The Wasting Sun. Relativity extends the human art of seeing the other person's point of view into the realm of physics and astronomy. In his social behaviour, each person is conscious of how his actions look to other people, and large pieces of his brain seem to be involved in this task. He relies on this awareness of self and others to avoid traffic accidents and brawls. Similarly, in the world of matter and energy, you can ask, for example, how the sun would appear to an astronomer in the vicinity of a distant star, and you would come quickly to the conclusion that it will itself look like an undistinguished star. More interesting effects arise if that alien astronomer is travelling at high speed towards the sun. Earthbound physicists reason that their white sun will turn blue from his point of view. A difference exists, though, between the social world and the realm of inanimate matter. Human beings and many other animals adjust their appearance and actions according to who is looking at them. Inanimate matter does not do so. It goes on behaving as before, regardless of whose telescope is trained upon it. Provided that the observation does not involve any significant interference, you do not expect to change the physical world just by looking at it. But the way it appears to you can certainly change. If an astronaut flies at high speed past the Earth, he is at rest from his point of view, with the Earth hurtling past him. He therefore judges the Earth to have enormous energy of motion. Of this, his colleagues on Earth are insensible. Therefore, it has to be simultaneously correct to say that the Earth has great energy of motion and no energy of motion. The astronaut's point of view is just as valid as the view of learned men confined to the Earth. When descriptions of the world disagree, the risk arises that the laws of physics specifying the behaviour of energy and matter may seem to be different to people travelling at various speeds. The astronaut might start predicting the Earth's behaviour differently. But no such rumination about appearances can alter the Earth's behaviour. It must continue to orbit steadily around the Sun, whatever the opinions of astronauts. The ideas of physics may falter, not the real world. But it should be possible to write down the laws of physics in such a way that their predictions remain correct regardless of the motions of the physicist. Not only is everybody's point of view equally valid, but all should agree on the essential features behind the appearances. That was Albert Einstein's project. To accomplish it, he was forced to do great violence to common sense notions about time, as later chapters will reveal. But one of his greatest discoveries, the equation E equals mc squared, involved such mind-troubling notions only obliquely. To follow him there, we need a little more than Doppler's effect, which changes the colour of light. To sail and be unaware of the ship's forward motion was for Lucretius and Newton evidence of relativity, antedating Einstein. But stronger ideas about the curious effects of travel developed with the advent of railway trains. Passengers on the Iron Road immediately noticed that even at breathtaking 60 miles an hour, when they were well aware of the joggling of the slightly uneven track, they could not feel any forward motion once the train has settled down to a steady speed. Rail travellers had the experience in a station of being momentarily uncertain whether their own train was moving or the one on the next track. Here were object lessons in the principles of relativity, that steady motion in a straight line is indistinguishable from being at rest, and that when two objects are passing each other at a steady speed, you can equally well say that A is moving past B, or B is moving past A. More subtly, when people listened to the roar of a passing train or to its whistle, the pitch changed. It went hee-haw, like a donkey. He during the approach, and haw when the source of sound was moving away. Now most of us, even if we noticed the effect, would shrug it off as no more significant than the rush of the wind and the rattle of the rails. But not Christian Doppler, a Viennese physicist working in the early 19th century. He won immortality by describing the effect carefully, extending it from sound to light, and pointing out that the change of pitch or frequency could be used to measure the speed of an object approaching or moving away from you, even the speed of a distant star. Okay, so we'll leave it there. But there we go. It's an interesting little book. If you can still find it, have a go. It might help you understand a bit better what is otherwise a very complex theory. But I hope you enjoy this one. Déjame saber en los comentarios, como siempre. But for now, we'll say cheerio.